All right, guys, this is going to be a quick summary of the history of atomic models. This is going to correspond to lesson 4 in your atom packet, and occasionally I'm going to refer to notes that you should write down that correspond to blank spaces so that you can refer to that later. So whenever I'm talking about the history of the atom, I like to start out with this picture. So this is the Eiffel Tower about 10 years after it had been constructed, and it's being struck by lightning. And lightning was seen as this kind of mysterious force, and charge in general, which is what lightning is, it's the buildup of charge, was seen as this mysterious force that only showed up every once in a while. It was kind of removed from everyday life. And one of the big ideas that I want you to take away from this quick discussion is that charge is actually fundamental to matter. So something that was seen as this mysterious force removed from everyday life is actually central to reality. Before we go any further, we've got to remember what's the golden rule of charge. And the golden rule of charge is that opposites attract and likes repel. And you guys already know this about magnets. If I bring a north pole and a south pole of a magnet together, they're going to attract. However, if I bring two north poles together, those magnets would repel. Same thing with two south poles. Now, the atom's a scientific model, and it's actually been in development for over 4,000 years. And we're going to talk a lot about models in chemistry. And a model is a representation of something in the natural world. In chemistry, they're often going to be used to describe things that we can't see. Models are often mathematical, and they're used to both describe and predict. So our model of the atom starts out with Democritus, who's a Greek philosopher from thousands of years ago. And he suggested that if he had an object, say a piece of paper, and he kept tearing it apart over and over and over again in half, he suggested that eventually he would reach a smallest piece that he could not divide anymore. And this idea of being indivisible is called atomos in Greek, and that's where we originally get the word atom. Now, this was more of a philosophical idea than an actual scientific idea for most of human history, really right up until the late 18th century. The man who turned it into a scientific model from a philosophical model, his name is John Dalton. So in the early 1800s, John Dalton conducted multiple experiments, including splitting water into hydrogen and oxygen, which I've done for you guys in class. And he turned this philosophy into a scientific model. And his idea, his mental image of the atom was that of an indivisible sphere. So kind of like the marble I have up there in the upper right. And his model was based on 4 premises. So premise number 1 is that all the elements are composed of tiny spheres called atoms. He said the atoms of the same element are identical and atoms of different elements are different. And we know even today that that's somewhat true. All atoms of the same element, for instance, have the same number of protons. He said that atoms of different elements can be mixed together physically, which relates to heterogeneous and homogeneous mixtures, which we talked about in the previous unit, or they can be combined chemically, which we talked about compounds. And those chemical combinations are always in whole number ratios. So hydrogen and oxygen are always going to combine in a 2-to-1 ratio to form water. And that's always true of every molecule of water. Finally, he said that chemical reactions occur when atoms rearrange. Atoms of one element never become atoms of another element. And we discussed that at the beginning of the year when we talked about conservation of mass. So Dalton took his experiments and came up with these 4 main ideas, many of which are still true today. Dalton's ideas were improved upon by a man by the name of J.J. Thomson in the late 19th century. He conducted something called a cathode ray experiment. So the cathode ray tube experiment involved a cathode ray tube, which you can see a diagram of it right here. It's basically a piece of glass where the air has been evacuated. And there's 2 pieces of metal here connected to a high voltage source. And these 2 pieces of metal, when the voltage source was turned on, would produce these particles, and these particles were detected. Later they would be known as beams of electrons, would be detected on this fluorescent screen. And this is actually how old school, say pre-2005 televisions worked. They had a cathode ray. And what Thomson did is he fired these rays And then he applied positively charged plates. And what he noticed was these electrons would bend towards the positive plates. These rays at the time would bend towards the positive plates. And going back to our golden rule, if these particles were bending towards a positive plate, that must have meant that they were negatively charged. So I'll show you a quick highlight of this. So again, this is what old TVs used to be made out of. And when the voltage was switched on, what would happen is these cathode rays would form a beam and would be detected on the screen. And what Thomson did is he did this with multiple metals and found this to be true. And what was really interesting is, again, when he applied an electric field. And when he applied an electric field and noticed that they bent towards the positive, he assumed that they were negative. So J.J. Thomson came up with a new model of the atom based on this experiment, and he called it the plum pudding model. And the plum pudding model is this idea that there is a positive diffuse sphere, which is most of the volume of an atom, and embedded within it are negative electrons. And I always make the analogy of a chocolate chip cookie. So most of the volume of a chocolate chip cookie is some dough, and embedded within it are chocolate chips. Thomson's model was improved even further by experiments by Ernest Rutherford. So Rutherford conducted a really famous experiment called the gold foil experiment. And in that gold foil experiment, what he did was he hammered out a really thin piece of gold foil, almost to the thickness of tissue paper. He surrounded that by a detection screen that would glow when radiation hit it. And he had a radioactive source that gave off particles called alpha particles, which are positively charged. And he directed them at the gold foil. And what he expected was, he expected those particles to go through the foil, because Thomson's model that we just talked about was this mostly diffuse, and diffuse means that there's not a lot of stuff there like fog. He expected these particles to go straight through. So what you're looking at right now is what he expected. What actually happened is just that. Most of them did go through, but occasionally some would be deflected. So they would either be deflected off course or they would actually be shot back at him. And if, again, you remember our idea of the golden rule of charge, if something is being deflected that's positively charged, it must also be encountering something that's positively charged. Right? This is an idea of likes repelling. So from that observation that those particles every once in a while were deflected, Rutherford came up with the nuclear model of an atom. And his nuclear model said two things. It said there's a dense positively charged nucleus in the middle, and that's where 99% of the mass of the atom is. And he knew it was positive because the positive alpha particles were being deflected by it. But he also said, hey, most of the volume must be empty space, because a large portion, in fact, the vast majority of the alpha particles actually went through. You can see that in this diagram. Most of them are going through. Every once in a while, one is being deflected. So again, his observation that 1 in every 800 particles got deflected back told him that the atom must be empty space, mostly empty space, and that every once in a while when a particle is colliding with something, it must be this small, dense, positively charged nucleus in the middle. Just to give you some sort of scale as to what this looks like, this is Phoenix's football field. It's newly completed football field. And if you put a quarter on the 50-yard line, the rest of the diameter of the atom would basically be end zone to end zone. So this nucleus that we're talking about is super small compared to the entire volume of the atom. So in conclusion, this model of the atom has been in development for thousands of years. And 3 of the 5 big models that you need to know for this class are Dalton's model, And remember, Dalton talked about an atom being an indivisible sphere. His observations came from various experiments, and he had his four main ideas. Thomson came up with the plum pudding model, and his main observation in his cathode ray experiment was that his electrons bent towards a positive plate, and therefore the electron itself must be negative. And then finally, Rutherford came up with what's called the nuclear model. He did the famous gold foil experiment, and the key observation in that was that most alpha particles went through, but about 1 in every 800 of those particles aimed at that gold foil were deflected back. And he concluded from this that there must be a dense positively charged nucleus in the center, but most of the volume of the atom is empty space.